Hello everyone, my name is Mohammad Rizal Kurim and I will be presenting our paper DeepHateExplainer, Explainable hate speech detection in under-resourced Bengali language. We know that the social media and microblogging sites not only provide platforms for empowering freedom of expression and individual voices, but also enable people to express antisocial behavior like harassment, cyberbullying, hate speech, and so on. Consequently, unlike other major languages such as English, hate speech in regional languages is also getting rampant and spreading across social media. In particular, being one of the most spoken languages in the world, Bengali is linguistically rich and has a lot of diversity. Therefore, hate speech in Bengali is being contextualized not only to the personal level, but also into religious, political, and geopolitical level. As hate speech is getting more pervasive, this can lead serious consequences and can promote violence, political, and communal conflicts. Therefore, identifying such hateful statements in social media and making awareness among people is non-trivial. On the other hand, identifying and hateful statement does not mean limiting or prohibiting freedom of speech, but keeping them from escalating into more dangerous level. Our research is backed by two important motivations. First, Bengali is severely low-resourced as it lacks computational resources. However, accurate identification of hate species not only requires properly annotated datasets and language models, but also efficient machine learning algorithms. Second, several machine learning and neural networks-based approaches have been proposed to accurately identify hateful statements, but mainly for resourceful languages like English. Recently, transformer language models have shown huge success across natural language processing tasks and clearly outperform both machine learning and neural network-based approaches. However, except for linear models, complex neural network architectures are mostly perceived as black box methods because of their not well understood internal functionality. For example, the following example clearly outlines a political hate, but we don't know why, making it a black box. To address the limitations of existing approaches and keeping in mind the motivating factors, we propose DeepHateExplainer, which is a novel approach for accurate and explainable identification of hate speech. In our approach, we classify the input examples into political, personal, geopolitical, and religious hates using transformer models. Subsequently, we we perform neural ensemble prediction of top models to improve the reliability of the hate speech identification. Then to improve then to provide human interpretable explanations of the predictions. Most important terms are identified using sensitivity analysis, and there was relevance propagations covering both local and global explainability. Finally, we measure the comprehensiveness and sufficiency scores to evaluate the quality of the explanations. To the end, DeepHateExplainer focuses algorithmic transparency and explainability. Since a properly annotated dataset is mandated for a supervised learning task, we prepared the largest hate speech detection dataset till date for Bengali by extending the existing Bengali hate speech detection dataset with additional 5,000 level examples. However, unlike unlike Bengali hate speech detection dataset that categorized observations into political, personal, geopolitical, religious, and gender abusive hates, we categorize them into political, personal, geopolitical, and religious hate, which is based on linguistic analysis that shows that often differentiating personal and gender abusive hates is really difficult. To the end, 8,100 examples are prepared covering political, religious, personal, and geopolitical hates. Followed by a set of comprehensive pre-processing steps, we consider training different transformer models to classify the training examples into different types of heads using each model, followed by the neural ensemble predictions. We perform cross-validation based on ensemble optimizations, followed by the majority voting ensemble of the top models. Besides, we train several machine learning and neural networks-based blind models. While machine learning models are trained using n-grams and unigrams with TF-IDF weighting settings, weights of the embedding layer of each neural network architecture is initialized with embeddings based on the fast text embedding models trained on 250 million articles. Since one of the main focuses of our work is improving interpretability of the hate space identification, we provide both local and global explanations in a post hoc manner. More specifically, global explanation is provided with the linguistic analysis and feature importance measure to highlight most important terms. The model put more focus on across the training examples. On the other hand, local explanation is provided to identify which features in a sample are important for individual prediction. And for this, we generated class-specific heat maps by employing layer-wise relevance propagations and sensitivity analysis in terms of leave one feature out experiments. While providing the local explanations of the predictions, an input statement is first classified where layer-wise relevance propagations identifies important terms by running a forward pass to the neural network based on the learned embeddings. In the backward phase, which is a conservative relevance distribution procedure, relevance is distributed from higher layer to the lower layer, in which most contributing higher layer nodes receives higher relevance. Finally, class-wise heat maps are generated to highlight the relevance for different types of heads, in which the color intensity signify their relevance scores. Finally, to measure the quality of explanations, we compute both comprehensiveness and sufficiency scores based on eraser benchmarks. Both of these methods are inspired by the concepts of rationals in which human annotators would highlight a span of text that could support their labeling decisions. For example, to justify why a review is positive about a certain movie, an annotator can highlight most important words and phrases that would recommend someone to watch the movie. Similarly, to justify why a review is negative, highlighting words and phrases that would tell someone not to watch the movie is also important. We performed several experiments. According to this table, the performance of machine learning baseline models was severely poor, making them not suitable for reliable identification of hate statements from the Bengali text. On the other hand, neural network baseline models also performed poorly compared to transformer-based models, although the fast text embedding models could have captured the word level semantics sufficiently. On a positive note, XLM-RoBERTa model turns out to be the best performing and best fitted model, giving an F1 score of 87, which is about 2 to 5% better than other transformer models. Bangla BERT-base and multilingual BERT uncased also performs moderately well. Then we assess if the neural ensemble predictions helps boost the hate space identification accuracy. We took top 3 models based on the performance metric and log norm for the FRS log norm of the PAL layer using weight-washer library. And what we observed is that ensemble predictions push the accuracy by at least 1.8% across the hate space classes. And with the F1 score compared to multilingual BERT-cased and XML-RoBERTa models. Thus, using ensemble techniques, the misclassification rate also reduced significantly. This signifies that ensemble predictions is effective to large extent at minimizing confusions among the classifiers. To provide global explanations, following terms features are identified based on linguistic analysis. As observed, terms such as Razakar, white criminals, Muslims, Jihadi, Samati Islami, Hor, execution, son of a base, bastard, broker, are most widely used terms often used to express different types of hate in Bengali. On the other hand, feature importance-based approach also identified more or less similar terms. Further, to provide local explanations, we provide class-wise example heat maps using layer-wise relevance propagations. As seen for this example, from the religion hate example in particular, words such as Muslim, Malaun, Hindu, Hatta means killing, and Puriye Mara are highlighted to signify that those are indeed more important and relevant terms for this certain example. To quantitatively validate the word level relevance for local explainability, we perform the leave one out experiment. As seen, this example is classified as religious hate with a probability of 59%. The model also thinks it could be of personal hate category with a probability of 30%. However, by removing the top words like Jati, Hindu, or Muslims, there is a sense that the prediction may be recourse or the probability distributions over the classes may be changed. Finally, for measuring the explainability, we considered only the top models. And what we observe is that gradient boosting freeze models shows both higher comprehensiveness and sufficiency scores compared to convolutional LSTM models or other transformer models. Although the convolutional LSTM models clearly outperform gradient boosting free models in terms of classification metrics. As for the BERT variants, Bangla BERT and multilingual BERT-base generates the least faithful explanations. This signifies that even a model attaining the best classification score may not perform well on unseen data, hence may not provide very faithful explanations. To conclude, in this paper, we propose DeepHateExplainer, an explainable approach for hate speech detection for under-resourced Bengali language. Our approach based on neural ensemble of transformer models can detect different types of hates from Bengali text with an F1 score of 88%, outperforming both machine learning and neural network baselines. Overall, our research made several contributions. First, we prepared the largest hate speech detection dataset for under-resourced Bengali to date. We are the first to employ transformer language models for hate speech identification, followed by employing ensemble of different transformer-based neural architectures. We provide comprehensive comparative study between our approach and the machine learning and neural network baselines. We employed interpretability techniques that will further encourage natural language processing research for Bengali. And finally, we provide a measure of explainability in terms of comprehensiveness and sufficiency. Our approach has several limitations too. First, we had limited amount of labeled data. Hence, we cannot confidently say we could completely rule out the possibility of overfitting. Second, we provided local explanations by applying sensitivity analysis and there was relevance propagations on best fitted deep neural network architecture baseline model. However, it would have been much reasonable to do the same on the best performing XLM-RoBERTa model. In future, we want to overcome these limitations and want to focus on other interesting use cases such as named entity recognition, multimodal hate speech detection, and question answering. Thank you very much for your attention. In case of question, you can file issues in this GitHub repository or email to the first author of the paper. Thank you very much. Thank you for listening.